Smart contracts are where blockchain rules become executable business logic. In this topic, we'll connect Solidity fundamentals to the way Besu networks run, govern, and deploy contracts, so your code is ready for enterprise use. You already have the foundation: Besu basics, enterprise architecture, consensus, privacy, permissioning, and a working development setup. Now we shift from understanding the network to writing the contract logic that will run on it, starting with Solidity fundamentals. In a Besu network, a smart contract represents shared business logic. Applications call it through Ethereum-compatible APIs, and Besu nodes execute it in the EVM. Because participating nodes run the same code against the same state, results are deterministic. That logic can define assets, approvals, registries, workflows, or compliance checks. In enterprise environments, contracts usually connect with permissioning, privacy, governance, and off-chain systems. At the code level, a Solidity contract works much like a class that lives on the blockchain. The license and pragma set legal and compiler boundaries. The contract declaration wraps the code. State variables store persistent data, functions read or change that data, events announce important activity, and modifiers enforce rules before functions run. After compilation, Solidity becomes EVM bytecode for Besu or other Ethereum clients, while the ABI tells applications how to call it safely. State variables are the contract's long-term memory. When a transaction changes them, that change becomes part of blockchain history, so storage choices matter. Simple types like uint, bool, address, string, and bytes, along with arrays, structs, and enums, each carry different gas and maintenance trade-offs. Marking a variable public gives you an automatic getter, which is convenient. Still, plan storage deliberately, especially for upgrades, security, and contracts expected to live for years. Every Solidity function needs two kinds of labels. Visibility answers: who is allowed to call this? Public and external expose behavior outside the contract, while internal and private keep it within the contract's code boundary. Mutability answers: what does this function do to state? View reads state, pure computes without state, and payable can receive ether. If a function changes state, users send a transaction and pay gas. If it only reads, it can often run locally. Modifiers act as reusable security gates around your functions. Instead of rewriting the same checks everywhere, you centralize rules like only owner, only admin, or when not paused. In enterprise Besu networks, this is important because different participants often have different privileges. Choose the right access model: simple ownership, role-based permissions, or multi-signature approval for high-risk actions. Then test the negative cases. Weak access control is not a minor bug. It can change state, move assets, or break governance. Events make contract activity visible to off-chain systems. When a function runs, it can emit an event into the transaction log instead of storing extra data in contract state. Listeners built with Ethers.js, Web3.js, or indexers can pick up those logs and trigger dashboards, alerts, analytics, or workflows. Index fields, such as an address or asset ID, make filtering efficient. Use events for meaningful business milestones while keeping required truth in state. For structured data, mappings and structs often work together. A mapping answers: given this key, what record do I get? That key might be an address, user ID, or asset ID. A struct defines what the record contains, such as owner, balance, status, metadata, or timestamps. Together, they support practical models like registries, profiles, assets, and approval workflows. Good design keeps storage compact, makes state easier to audit, and leaves room for future upgrades. A smart contract should be treated as a governed software product, not a one-time deployment. It starts with requirements, design, coding, and local tests. Compilation turns source code into bytecode and an ABI, and deployment uses those artifacts to create an address on Besu. After that, applications invoke the contract, teams monitor behavior, and changes follow controlled upgrade or migration paths. Eventually, a contract may be retired. Testing, governance, and release management protect every transition. Before deployment, Solidity source code must be compiled. A compiler such as Sulk, Hardhat, Foundry, or Remix produces two key artifacts: Bytecode is the machine-readable instruction set deployed to Besu and executed by the EVM. The ABI is the contract's public interface, telling applications which functions, inputs, outputs, and events are available. For reliable deployments, keep compiler and dependency versions pinned, so builds are reproducible. Runtime interaction has two main paths: calls and transactions. A call asks the contract a question. It reads current state, returns a value, and does not create a block or spend transaction gas. A transaction asks the network to change state. An account signs it, a Besu node receives it through JSON RPC or a library validator's order and execute it, and the receipt reports status, gas used, logs, and events. Because deployed contracts are immutable, upgrades must be planned before production. Suppose an asset registry version 1 needs new compliance fields. The team might redeploy, use a proxy, or migrate through a dedicated contract. But every choice needs version records: source code, compiler, ABI, address, and approvals. Retirement is also controlled. Old functions may be paused, disabled, or migrated, with inactive records clearly marked. The goal is governance plus auditability, not improvisation. Gas is Besu's execution meter. Every EVM step consumes a defined amount, and the transaction gas limit acts as the safety stop that prevents runaway contracts. On public networks, gas connects directly to market fees and real cost. In private or consortium networks, you may reduce or customize the economics, but gas still protects resources and controls execution. Optimize storage writes, loops, and heavy computation, because inefficient contracts can fail or slow the network. You've built the Solidity foundation for Besu, defining contract state and behavior, controlling access, emitting events, and managing execution across the contract lifecycle. Keep gas and transaction behavior in mind, even on permissioned networks. Next, you'll deploy contracts, connect them with Web3.js or Ethers.js, and shape enterprise-ready solutions.